Alright, so let's do a quick roll call and then we'll start. So we have Anjani, Dhanvin, Neil, Nishka, Purvi, Riya, Ritika, Saranya and Vishal. And in the classroom we have Daivik and Arush. And few of the kids are not joining today, but they will have to watch the video. That's an extra responsibility for the kids who are missing the class. So we'll talk about similarity of triangles, we'll talk about SOHCAHTOA, we'll talk about trigonometric ratios, and then we will also look at how do we derive those values. Okay, Daivik is thinking something. You want to say something? Okay. And don't feel shy, right? Okay. Sometimes what happens is you are thinking something and you are laughing at it, and you are having the guilt that okay, the class is going on, I'm laughing. People will think that okay, what this guy is doing. We can take a 2-minute break and vent out your feelings, and then we'll talk about things. Okay. So we talked about congruence in the previous classes. Are we all very, very, very clear about what is congruence? What is meant by congruence? Go ahead.
It's like two sides or two shapes. Or anything is just equal.
Any two things which is exactly copy of each other. Like two A4 sheets. Like two triangles with matching dimensions. Yeah. So, and Nishka, you are going to be the victim of today's class because I'll ask a lot of questions to you just to understand if there's something that that you are aware of, because I have covered that in the class which you have not attended. So don't feel that I'm putting you on the spot. The idea is just to get a sense of what is your comfort, what are the things that you are aware of, what you would want me to explain better. Okay? So don't feel that okay, I'm kind of giving you extra treatment, or I'm trying to put you on the spot. Okay? Alright. So when we say congruence is nothing but equal to, if I say that way, right? And when you talk about any geometrical shape, when you say two shapes are equal to each other, these two shapes cannot be congruent. By no means, because their properties are not matching. So when you say congruent, meaning that each and every property have to match. Here you have 3 sides, here you have 4 sides, out of question. This is not a scenario where you will even bother to think about congruence between these two shapes. Okay? Only these two shapes can be congruent. Okay? When I am talking about triangle and a triangle, only the triangles can be congruent with each other. Whether they are congruent or not, that we will check and we will figure out. But is that the same understanding that we all have? Ritika, Riya, everybody, right? Yeah? Saranya, Dhanvin, everybody? Yeah? Purvi, no doubt, right, beta?
Yes, sir.
And be assured, Nishka, I treat everybody in this class like a child, so you'll be one of them. Yeah? So if I say kids, beta, son, whatever, it's all the same. Okay. Now, so when we talk about congruence, what if I say these two shapes are congruent? That means I have zero doubt about they being exactly a copy of each other. When are two things copy? When each and every side matches. This side matches with this side. This side matches with this side. This side matches with this side. This angle matches with this angle. This angle matches with this angle. This angle matches with this angle. That is the point when I'll conclude that these are congruent. Yep. For the triangles. Similarly, you pick up any shape. When you say congruent, that means they are a copy of each other. No doubt so far, right? Let me not beat this drum any further. Why I was talking about congruence was because the concept that we'll talk about today is related to that, but an extension of it. Now look at this. Will there be a possibility of these two being congruent optically? I mean, forget about the mathematical concept. Do you think these two can be congruent? Both are triangles, both have 3 sides, both have 3 angles. Can they ever be congruent? Or do they look congruent? Ludev? Yes, Dave.
Did I miss anything?
I'm sorry, beta?
I said I'm like sorry for joining late. Did I miss anything? So
No, we are just starting. So I was blabbering so far. Don't worry about it. So today we are going to talk about concept of similarity. We'll talk about Pythagorean theorem, and then we'll start with our journey on trigonometry. Okay? And I need your help. Can you close the garage door?
It's the upper one. Right?
The upper one. Yeah. Yeah, Purvi.
I feel like the triangles are similar but not.
You are guiding me in the right direction with that. Okay? So these two, unless I am totally blind, I'm half blind though. Can everybody see the board? Yeah. I'm half blind because I can't manage good without glasses. So anyways, I'm not trying to offend anybody who's wearing glasses like me, but yeah. With my naked eyes, I can see that they cannot be congruent. This looks much smaller, this looks much bigger. Okay? And when I say bigger or smaller, I'm saying that this side looks much smaller than this side. This side looks much bigger than this side. Let me keep the story straight. This side is much smaller than this side is much smaller than this side, and this side is much smaller than this side. So by no means, optically I don't see them being congruent. And when you take a scale and measure it, you'll come to the same conclusion, that they are not congruent. Okay? But there is another property called similarity. They look to be similar. Now, what is the best possible example of similarity that you guys deal with every day, every hour, every minute, every second when you are dealing with a phone? Anything that relates to the concepts of similarity when you are dealing with a phone. How many of you don't use that zoom in, zoom out functionality of a picture? When you see a picture, you do zoom in to make it look bigger. You do zoom out to make it look smaller, right? So let's say I have a triangle on my phone, okay? A picture of the triangle on the phone. When I zoom in, you will see it becoming bigger. When I zoom in further, it becomes bigger. If you want to relate that with mathematical concepts, this is the concept of similarity. When you are making things bigger, smaller, what you are doing here is, you are keeping the angle same, but the sides are increasing. If you look at this triangle, when you zoom in, it will not become like this triangle. The shape will look similar. Only the dimensions, the sides will keep on becoming bigger. Am I kind of making sense so far? Purvi, Nishka, Riya?
Yes.
Yeah, making sense? So this zoom in, zoom out that you see, if you want to relate that mathematically, you will see that, and you can safely say that it's a concept of similarity. Now when you talk about similarity, what it means is, the inclination of the side, the angle between the side remains the same. Every side, these two sides, this angle remains the same. If you zoom in something or zoom out something and keep measuring the angle after zooming, zoom out, you will see the angles remain the same. It's only the side that changes. It keeps on expanding. Okay? So, now another stupid example could be all of us. When we were small, when I was 2-year-old, that was 47 years ago, I am a zoomed in version of myself compared to that age. All of you. You all are zoomed in version of yourself from your younger age. Yeah? So, that is what is similarity. Now, if you go do a further deeper dive into it, one thing is for sure, that when you zoom in, your angles remain the same. Only the side keeps on expanding. Now, How are they expanding? Let's look at an example of, let's say, triangle. Since we talked about congruence of triangles, and if I am assuming that you guys all are familiar with these 4 theorems of congruence. These 4 theorems of congruence of triangles. If not, you guys can look at it again, but today we are not talking about congruence, so we are not going there. But we are going to talk about similarity. If I am saying these 2 triangles are similar, either this is zoomed out version of this guy or this guy is zoomed in version of this guy. Yeah? What you know is this angle, if this is angle 1, this is also same as angle 1. This is angle 2, this is also same as angle 2. This is angle 3, this is also angle 3. So the angles will remain the same. You pick any closed shape, keep zooming in, zooming out, the angles will remain the same. Okay? Only the side changes. How?
Because it's getting scaled.
Yeah, it's getting scaled. So my question to you guys is, how is that changing? Again, can you tell me mathematically? If I say these 2 triangles are similar, meaning the angles are matching, it's zoomed in, zoomed out version of each other. What is the relationship mathematically between the sides? Angles we know they are same. Yes, Dave. I'll come to you. Yeah, Dave.
Wait, so like
No, so and see, you can by default assume this is angle because the angles are matching. Okay? I'm trying to find out the relationship between the sides. If the 2 triangles are similar, what is the relationship between the sides? Yes.
The sides are proportional.
Sides are proportional. The ratio of the sides are the same. Okay? Now look at, let's say, this triangle A, B, C, and this is C. Let me make it small a, small b, small c. Okay? We have 2 triangles ABC and ABC. This is capital ABC and this is small ABC. Is everybody able to see the board okay? You guys are better off. I'm talking with the kids on the screen. Okay. Now, so these 2 triangles are similar, meaning this angle 1 and this angle 1 are same. This angle 2 are same. Angle 3 are same. So what? So what Divik said is their sides are in the same proportion, or they are proportional. How do I put that mathematically? What do I mean by that? Now look at this. So I am giving you the clue. Now these 2 triangles are similar because this angle and this angle are same. Okay? That means the side opposite to the angle. So this side opposite to this angle 1 is AC, and side opposite to this angle 1 is small AC. This will be equal to, pick the second angle which are same, second angle. Side opposite to that is BC. Side opposite to this is small bc. Third angle, these 2 are same. Side opposite to that and side opposite to that. Side opposite to this one is AB. Side opposite to this is AB. This is what it means. When you have 2 triangles similar, their sides will be the same proportion, meaning the ratio of the sides of the matching angles will be same. I will let you guys take 30 seconds to digest this before I move on. Yes, Purvi.
Wait, so if you like switch the so if you put lowercase AC on the top and uppercase AC like on the bottom, would it still be the same? Just a different
No, you will flip everything upside down. You will flip this guy, flip this guy, flip this guy.
Okay,
Because
okay.
1 by 2 is never same as 2 by 1. Correct?
Yes, sir.
Okay. I know I keep on giving stupid examples, but bear with me. Hey, Rehan. Does it make sense to everybody? Okay. Ria, Rehan, Dave. Rehan, you joined a little late, but we just started talking about the concept of similarity. When we say similar, when I'm saying this triangle and this triangle are similar, I'm saying they have matching angles. So 1 and 1 matching, 2 and 2 are matching, 3 and 3 are matching. And what geometry says is, if you have two triangles similar, their sides will be in the same proportion, meaning side opposite to the matching angles. So side opposite to this is this one AC and side opposite to this one is small AC. Ratio of this will be same as the ratio of the second matching angle. So this angle and this angle are same, side opposite to that, BC by side opposite to this small bc. It will be equal to the third one. Okay? Is this concept clear to everybody? Shravya, are you with me? Dhanvin, no questions? Dave, Ritika?
I listen, sir.
Okay. Shiv and Vishal? Okay, good. Now, why I was beating this drum so much so? Because I'm going to talk about, before I move on. So now the only takeaway is, if you are talking about two triangles being similar, you are talking about angles matching, only angles matching. When the angles are matching, the sides will be in the same proportion. And again, when you are talking about sides, you look at sides opposite to the matching angles. Okay? So this is your triangle A, this is triangle B. If you are saying these two triangles are similar, you will pick up the three angles, and pick up the matching angles side opposite to that. That ratio, second matching angle side opposite to that, third matching angle side opposite to that, will be the same ratio. Okay? That is the takeaway. So similarity ensures that the angles match and the ratio of the sides opposite to those matching angles match. Yeah? Ratio match, not the numbers. So that is why if you look at this and this being similar, or when you zoomed in this one and got this one, what does it mean? Let's say this is 3 centimeter, this became 9, this is 4. So this is similar, meaning this side increased by 3/4. That means this side will also increase by 3/4. If this is 5, then this will become 15. Everything is increasing by 3/4. That's why when you look at the camera, it says zoom by 2x. You are increasing every side 2 times. Zoom 5x. You are increasing every side by 5 times. Yeah? Is it relatable? Now, if you look at any camera zoom features, now you are going to relate that to the concept of similarity. Yeah? Making sense to everybody? Okay, let's move on. So this part we saw. Now, all of us, some of you call me uncle, some of you call me sir, some of you can choose to call me Mr. Biren, whatever you are comfortable with. But all of us have one common uncle. All of us. Do you guys know the name of that uncle? Pythagorean's uncle, who has given us one formula called Pythagorean Theorem. And that Pythagorean Theorem applies for a right angle triangle, which says if you have a right angle triangle and these are the two sides making the 90-degree angle and this is the hypotenuse, a square plus b square equal to c square. This is a theorem that all of our uncles, no, not all of our uncles, one of our common uncle has given. I am too old to call somebody uncle, but just for the sake of some convergence here. So this says, Mr. Pythagoras, he had given a theorem called Pythagorean Theorem, which says in a right angle triangle, the square of the two sides, sum of the square of two sides, which is making 90 degrees, is equal to square of the hypotenuse. But what? I am not an easy nephew who will agree to anything that any uncle says. Do you guys know why this is true? Purvi, Nishka, Riya, anybody, has anybody come across why this theorem is to be believed? Because I am a very bad student, okay? I never believed in any theorem blindly, and I don't want you guys to believe it either. Yes, Shiv. I'll continue now. Yes, Shiv.
So, sir, the explanation for why the Pythagorean theorem would be true is because a square would be, if you turn each side into like a big square, right? So like a would be the side length of one square, b would be the side length of another square, and c would be the side length of another square. If you do like squares on the sides and then you made it into like that, then the area of the a square and the area of the b square, when you add those numbers together, you get the area of the big C square, which is the long side.
So that is the practical way of doing it. I am looking for a solution for mathematical way of proving it. Okay? Because what you said, that will be a practical example of it. But I'll come to that later, okay? So yeah, Arush, you were saying something. I'm sorry, same thing? Now I'm telling you that all that non-stop talk I did for last 20 minutes was the root of this. The concept of similarity has derived this formula. So it's not that Mr. Pythagoras was sleeping and then he got a good dream and after he woke up he wrote this formula. It was derived mathematically, and that's what we look at right now. Okay? So this concept of, this Pythagoras theorem is based on the concept of similarity. Okay? Shall we start? Shall we look at the magic behind the Pythagoras theorem? Let's say this is my right angle triangle. This triangle will be called a right angle triangle because this has one angle which is 90 degrees. Okay? And let's say this is A, B, C. And the side opposite to that is called hypotenuse. Let me not give it A, B, C because this will create confusion. Let's say it's P, Q, R. Okay? So I have a triangle PQR, which is a right angle triangle. This angle is 90 degrees, this is hypotenuse. Okay? I will call this as A, this is B, and this is C. What we have to validate is the correctness of this theorem given by our uncle. Yep. Is everybody okay with the problem statement for now? Okay. Now, how do we figure it out? I don't have anything given to us, okay? So, what we'll do is, let's say, we draw a perpendicular from here to here. So, this is 90 degrees and this is also 90 degrees. Okay? PQR, let me call this as S. So, what we did was, we had triangle PQR from point Q, which is which is making the angle 90 degrees. I have got a perpendicular on the hypotenuse, which eventually converted this to, we split this triangle into two small triangles. Let me give it a color, because color makes it colorful. And just a bit up for you, just to be aware or beware. I crack a lot of dad jokes, bear with me, okay?
Okay.
Okay. So we have a blue triangle and a green triangle. And how these two came into light was because we had a right angle triangle. From here we draw the perpendicular, we split this into two right angle triangles. Yeah? Everybody with me so far? Now, let's take the blue triangle. So, what I will do is, I will call this a black triangle and call this a blue triangle so that you can visually compare what I am saying. So, my blue triangle is PQS. PQS. Okay? And my black triangle is PQR, the original one. Are you guys able to relate to it? Yeah? Rehan, Shiv, Vishal, everybody, right? Okay. Now, and I keep randomly calling out names, okay? Doesn't mean that I'm ignoring anybody. I'm just randomly picking names. So I have blue triangle, this one, and I have a black triangle, which is the full triangle, the parent triangle. What I'm saying is, my blue and my black triangles are similar. Why? Look at the blue triangle, okay? Blue triangle and black triangle both have angle QPR, or I will say QPS. Both have, see, look at the blue triangle and look at the black triangle. Both have this angle common, right? One angle is common in both the triangles, correct? Is that making sense to everybody? Between the blue triangle and the black triangle, this angle is common any which way, correct? So one angle is common. Now, both have 90-degree angle. So this guy has another angle 90 degree. Let me say black one. Black one's 90 degree is PQR, and blue one's 90 degree is PSQ. Am I making sense so far? See, look at the blue triangle is this one, black triangle is the whole one. Both have this angle common. Yeah? And the blue triangle has this angle is 90 degree and the black triangle has this angle is 90 degree. So two angles are matching in both the triangles, between the blue triangle and the black triangle. They have two matching angles. Yeah? Do they have the third angle not to match? Okay. Sum of all the angles of any triangle is always 180 degree. Yeah? So when you look at this blue triangle, it has this angle, and the black triangle also has this angle. This is common. This blue triangle has this angle 90 degree and this black triangle has this angle 90 degree. So they have two angles, they are matching with each other. That means the third angle has to match because sum of all the three angles will be 180 degree. So the theory that I was forcing on you guys, that this triangle and the last triangle is, these two are similar. Is it making sense now? Yeah? Repeating one more time. So I had a right angle triangle. From here I dropped a perpendicular on this hypotenuse. We split this into two triangles, the green triangle, the blue triangle. Right now we look at this blue triangle and the original triangle, and we found that this angle is common between both of them. This blue triangle has this angle 90 degree, the last triangle has this angle 90 degree. So two angles are matching, so the third angle has to match any which way. So if the three angles are matching between two triangles, now we visualize this. Your blue triangle is like this. Your blue triangle is like this, and your black triangle is like this, and this angle is matching with this guy. This angle and this angle are anyways common, same angle. So this angle and this angle have no choice, they are matching. Yep. Is everybody with me? Purvi, Shiv, Saranya, Dhanvin, Riya, everybody? Rehan? Yeah? Okay. So now we found that this blue triangle is similar to the large triangle. Now when the two triangles are similar, what did we learn just 10 minutes ago? The sides are in the same ratio. Meaning the sides opposite to the matching angle will be in the same ratio. So now let's do one thing. I will not get you guys confused here. I have made a picture of these two triangles, right? So this is blue triangle. So this is P, S and Q. It's like I've taken a copy of it. And this is P, Q and R. Okay? Where this is, let's say this angle is 1, so this is also 1. This is 2, this is also 2, and this is 3, this is 3. Okay? This will help us find out the sides. Okay? The ratio. Now, when these two triangles, we are saying that they are similar, their sides in the same ratio. Let's pick up this as a numerator. So side angle 1 and 1. Side upward to that. Side upward to this one is what? QS. QS divided by side upward to this is QR. Okay? Will be equal to, take the second angle. Let's say this one. Side upward to this one is PQ divided by side upward to this. This is 2. Side upward to this is PR. Okay? And the third one will be this angle and this angle are matching. So side upward to this is PS divided by side upward to this one is PQ. Okay? So from this blue triangle and the black triangle combination, what did we find? We found this relationship. QS divided by QR equal to PQ by PR equal to PS by PQ. Okay? Yeah? Don't worry about taking notes, okay? And just focus on what I'm doing, okay? Because you guys can prove it 100 times if you are very clear. Now I'm changing my plan. I'm going to the green and the black triangle. Meaning, again, same way, I'm saying this green triangle is similar to the original triangle. Do you guys agree? This green triangle is similar to the original triangle. Why? This angle is anyways common. This triangle also has 90 degree. Same as this one, third angle. This angle will match with this angle. Yeah? Look at this. This is your green triangle. This is your green triangle. This was Q. So this was green triangle Q or S. And your black triangle was R, P, Q. So this angle and this angle are matching. This angle is 90 degree and this angle are 90 degree. These two are anyways matching. So the third angle is left with no other choice. Yeah? So these two triangles are also similar. Digestible or difficult to digest? Yeah? Ria, Ritika, Dev. Neil has not said anything today. Neil, is this okay with her? Saranya, okay? Okay. Okay. So basically what summary of that is, when we have a right angle triangle, we drop the perpendicular from this corner where we are making 90 degrees to the opposite side. It split into two right angle triangles, and this triangle is similar to the original triangle. Similarly, we are finding that this green triangle is also similar to the original triangle. All the three angles are matching. So when the angles match, they are similar. That means their side will also be in the same ratio. So if this is angle A1, this is 1, this is same as this one. This is 2, this is 2. Careful, careful. This is 3, this is 3. And see, look at what is that extra care I'm enforcing here is, we have to be very clear about which angle is matching with whom, because the ratio of the side is determined by that matching angle only. Now if you look at this one, here, since these two triangles are similar, the sides will be in the same ratio. Let's pick this as a base, as the numerator. So, I mean, we can pick this also. If you want to pick the smaller triangle as the numerator, that is also okay. 1 and 1, these two are matching. Side upward to this and side upward to this will be RS divided by side upward to this is QR. Will be equal to second angles ratio, second angles upward side ratio. This is second angle to, this one is QS, and second angle is this one, is PQ. Will be equal to third angles ratio, this one and this one. Third angle is this one, side upward this is QR. Third angle is this one, this is QR, and third angle is this one, right? PR. So now we have two equations. From this whole gymnastics that we were doing so far, we found these two relationships. So let's pick these two combinations, okay? If I pick, why I'm picking this? Because when I do butterfly, I get a PQ squared here. Okay? So from this I get PQ squared equal to PR into PS. PS. Okay? Now look at okay. Now I will pick these two here. What did I do? I don't have an option of doing Control Z. But anyways, don't worry about it. Don't worry about it. I will see what is that we are trying to do. This square plus this square. So that's why from this combination I picked something that gives me a PQ square, and this was my combination. Similarly, from here I picked up something which gives me a QR square. So PQ square plus QR square, we want to see whether that is equal to this or not. Yeah? So this gives me, by butterfly here, we get QR square equal to PR into RS. Yep. So PQ square, and now I am saying this PQ is A and this is B, so that I don't have to write that much. PQ square plus QP square plus QI square, so A square plus B square equal, I am just adding them. It becomes PR into PS plus PR into RS. Now PR is common, so take PR common. PS plus RS or SR. Can I say that? PS plus SR. What is that? PR. So PR plus, PR into, this whole thing is PS plus SR or RS, whatever you call it, into PR. This plus this becomes PR. What did you get? This is PR square. And PR square is nothing but your C. Now everybody is probably confused or doing that calculation to figure out how did this old man come to this formula. Right? Summary of this is simple, very simple. Okay, don't try stressing yourself too much. This was your right angle triangle. What you did was you dropped the perpendicular from here to here, which split this into two right angle triangles. I mean, look at this right angle triangle and compare that with the original triangle. You found this angle is same. This angle is, this angle is common between this triangle and this triangle. This is 90 degrees, this is 90 degrees. So two angles are matching, third angle will match. So this triangle is similar to this triangle. Similarly, you found this triangle is similar to this triangle. Now, when this triangle is similar to this triangle, you found this ratio. This is similarity formula, right? when this triangle is similar to this triangle, you found this ratio. There's something here which I created, which you guys can watch in the video. Now when you had this thing, you had all these ratios. Now you're trying to figure out how you want to derive this formula. Ultimately, you have to find out this and this square. Now you look at this combination, this equal to this equal to this. That means this equal to, I'm sorry, PQ. And we found that, okay, if I take this combination, I can get PQ square. So you took this combination. Similarly here, when you saw this, okay, I can take these two combinations, I can get PQ square. So you took these two and you took these two. From this you got PQ square, from this you got QR square. So PQ square plus QR square. And you just added them, you did not do anything magical. Yeah? And that eventually got you to validate what Pythagoras said is trustworthy. Yeah? Is it, or did it make sense to everybody, or I was just talking to myself? Purvi, Shiv, Saranya, Vishal, Dave, everybody clear? Dhanvin, Ritika? Okay. So, now the question that you guys will have in your mind is, whatever time we have wasted trying to prove that is already proven, was it worth it? And the answer could be yes and no both. Would anybody ask you guys to prove Pythagorean theorem? No, nobody. Do you need to understand the underlying concept? Yes. Now, I got my first phone when I was in the third year of my job. Phone was evolving, slower than I was evolving. So, but now if you look at the kids, toddlers, who are still dealing with diapers, they know how to operate the phone. And they know zoom in, zoom out to see the pictures better. That is based on this concept. Right? So, why we are learning this or emphasizing this is because this concept of similarity is not only helping us revalidate the Pythagorean theorem, but it will be one of the important concepts that will come across in your SAT exam also. You will see that there are questions where you have a couple of triangles to deal with, and then you have to find out there are certain things that is known, certain things that are not known, and you have to use these concepts to relate and find it out. Okay to digest or believe? Ria, right today? I took Mr. Pythagoras head on just to make sure that you guys believe in that theorem in a better way rather than memorizing it. Yeah? Neil, okay with that? Rehan, any doubt? Okay. Saranya, all clear? Shall we move on? So, before we move on, right, we have only 14 more minutes. I want to do a quick recap. What all did we learn and how are they relevant to each other? How are they relatable to each other? First thing was concept of similarity that we looked at. When you look at similarity, that simply means how do you zoom in, zoom out? How the shapes, or when the shapes are called similar, when their angles don't change, but the sides change. Now, a counter question or argument that you might have is, it's fine when you're talking about closed shapes like rectangle, triangle, pentagon, whatnot. How about this one? The buttu. That's what you call it, buttu, right? Buttu in Telugu, right? One of my kids told me, what is it called? Okay? In Hindi we call it bindi. So this is called buttu in Telugu, right? Okay. So this shape, which is a circle, neither you have angle, nor you have side. How do you relate that to the similarity concept? the only property that you have here is the radius. That's the only thing that determines your circle. So when you are talking about zoom in, zoom out, here like your side changes in a certain ratio, in a certain but gets multiplied by a certain number, here your radius gets multiplied by that number. Okay? So when you are zooming in, let's say your camera says 2x. Okay? So that means if you are looking at a circle of radius 5, you can expand it up to 2 times 5 radius circle. Yeah? So now we could relate this similarity concept with what we see on a day-to-day basis also. And then we looked at Pythagorean theorem. Everybody knew Pythagorean theorem. I will not claim that I taught you guys what is Pythagorean theorem, but I will certainly claim that I kind of gave you guys a little insight into that, to say if you come across any theorem ever, it is always worth to check why did that theorem come into existence and what is the underlying concept. Because math is about how much you can dig. More you dig, what do you get by digging?
Understanding.
When you dig, you potentially can get some mines. When you dig, right, you get gold, you get diamonds. So here when you are digging the math concepts, you get the underlying $1 million principle which is actually the root of this thing, right? So anyway, that was another dad joke. Let's move on. So next thing that we'll talk about would be, I will probably not start that, but this right angle triangle, it might look cute. If this is not looking cute, this will certainly look cuter. But there's a lot of concept around it which has given birth to a new subject by itself, which is called trigonometry, right? And it all revolves around this triangle, right angle triangle, right? While you guys have heard about 6 different types of triangles, based on side you have equilateral, isosceles and scalene triangle. Based on angle you have right angle, acute angle and obtuse angle triangle. But one of the 6 is the most powerful of the 6 that we know of. And that is the source of the subject trigonometry. Trigonometry. I mean, sometimes I feel my accent has a lot of influence from my roots, but then bear with it. So trigonometry, when we talk about, that revolves around this one. And this is where we'll talk about the ratio, the trigonometric ratios, sine, cos and tan, and we'll go into the details to figure out how the value of certain angles. We'll try filling out this table, okay? Sine, cos, tan, 0 degree, 30 degree, 45 degree, 60 degree and 90 degree. How are the value for these different angles are derived? Because by now, Niska also, you would have realized that this teacher doesn't believe in anything that is said unless we see it by ourselves, right? So we'll derive the value for these angles. Like if I can put it, sine 0 is 0, sine 30 is 1 by 2, sine 45 1 by root 2, sine 60 root 3 by 2, sine 91 1, root 3 by 2, 1 by root 2, 1 by 2, 0, 0, 1 by root 3, 1, root 3 and infinity. This table I just filled, but I am not going to ask you guys to memorize this. We will derive all these values mathematically so that you will have a recorded evidence in the form of a video of what you see here and how are these derived, so that tomorrow, if you see again, the reason why I keep stressing on the origin of these things is because if you know the underlying concept, you can relate to it a lot of things and you can derive a lot of things by yourself. everything that I'm teaching you guys, probably you may or may not find that in the books. Yes, Vishal.
Isn't sine of 45 degrees 2 by square root 2?
2 by square root 2, no, it's 1 by root 2.
Square-
Sine 45,
Isn't it square root 2 by 2?
2, say that again?
Square root 2 by 2?
Square root 2 by 2, yeah, same thing, right? The square root 2 by 2
Oh yeah, yeah.
is the same thing. Yeah? So, anyways, I mean, whether it's 1 by root 2 or 2 by 2, 1 by root 2, we'll derive it, okay? Because I don't feel comfortable if I'm not explaining these things to you guys. So that when you are in the examination hall and you are getting stuck with memorizing the formula, and if you have to derive it yourself, you should be capable enough to do that, and that you can do only if you are very, very clear about the underlying concept. So here, I'm not rushing for completing the syllabus, but I'm rushing for making sure that each and every concept that we learn, you go out very confident of the class. If you just, after the class, if you think that, okay, the teacher told something, but I don't know, this guy is getting old and he is forgetful, he keeps blabbering, we are not able to argue with him, so we have to believe him. That will never be the situation for any of you. Alright? So, I'm not going to this one today. Only thing I want you guys to recall, which I believe you already do.
TOM.
Cool. Okay, yeah. But I was just, what is cosine starts with C or K? So now you guys can figure out how poor is my English, right? I was wondering, cosine starts with K or C. That's what I was struggling with for 10 seconds. But thank you so much. So back to a sine, cos and tan. How do you represent in trigonometry? Just try recalling that. I'm sure everybody remembers it. If not, we'll anyway go through it tomorrow, and then we'll look at deriving these values mathematically with enough proof, with enough confidence. That is all we had for today. Any questions before I let you guys go? And this guy, as I told you or warned you, you'll be the obvious victim of the class because this is your first class. Did you, were you able to follow whatever I said, and did it make sense to you?
Yes, I did, sir.
Okay, cool. So that's my takeaway, right? I mean, when I teach something and I hear a confident yes, that makes me believe that I'm doing okay with respect to what I was supposed to do. Anybody else in the class who has any doubt? Ria, Rehan, Neil, Danvin, Dave, Ritika, Saranya, Shiv, Vishal, anybody? Guys, you have 5 minutes to fight, argue with me. Let me get a quick feedback from all of you. Is this approach making sense to you guys? Yeah? Everybody on the screen? Is this approach helping you retain things for a longer time? Yeah?
Yes.
Okay. That is what we'll do. And I'm going to be standing for next 2 more hours teaching the younger kids. That is not because I'm doing any workout right now. It is my passion for the subject, and I'm just trying to inject that passion in each one of you. If you enjoy math, I can retire happily. Okay? That's what we're working on. So keep enjoying math. Whatever we do in the class, after the class also try doing some practice. Try finding out some difficult problems. Share in the group. Challenge your friends. Share with them. Say, okay, fine. Do you know how to do it? Can you tell me a better approach? When you discuss, debate, argue, math becomes more interesting. Alright? So thanks everybody. I'll let you guys enjoy the rest of the evening. I'll come back haunting you tomorrow same time.
Thank you.
Alright. Bye-bye. Take care. Bye-bye. 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 Bye dear. Okay.